Welcome in Core. Previously, we talked about how astronomers have confirmed a new interstellar visitor, 3IATLAS, only the third ever seen. While NASA calls it a comet, astrophysicist Suzanne Forstner suggests it could be a planet seed, helping young stars form giant planets far faster than dust and gas alone. In this video, we'll explore three things. What makes it different from ordinary comets? How Forstner's planet seed theory could solve the mystery of giant FAMs forming so fast. What does this idea mean for how these are born? The discovery and the problem 3IATLAS was identified by its unusual path through the solar system. Instead of the closed elliptical loops of local comets, it followed a hyperbolic trajectory, meaning it entered from interstellar space and will never return. That puts it in the rare company of Oumuamua and 2I Borisov, the only other confirmed interstellar visitors so far. Each of these objects challenged expectations. Mua accelerated in ways that didn't match standard cometary behavior. Borisov looked more like a textbook comet, but had unusual chemical traits. Now, it adds to this small but growing sample, showing signs of comet-like activity, but with irregularities that keep scientists cautious. Most researchers lean toward a cometary explanation. The physics of volatile ices heating near the sun can produce jets that nudge objects off course, but the oddities of these visitors keep the door open to alternative thinking. Harvard astrophysicist Avi Loeb famously suggested alien technology, though without direct evidence that remains speculative. For many astronomers, the biggest scientific opportunity lies not in exotic possibilities, but in asking whether interstellar objects play a broader role in the galaxy. This connects directly to a long-standing puzzle in planetary science. How do gas giants form so quickly? The standard accretion model says planets grow gradually as dust grains collide and stick, eventually forming planetesimals and then planets. But simulations reveal a barrier. Once particles reach sizes of centime to meters, they tend to bounce off each other or fragment rather than combine. This makes it hard to scale up to massive them within the limited lifetime of a star's protoplanetary disk, which typically disperses in under 10 million years. Telescopes reveal giant them around stars just a few million years old, too fast for standard models. 3IATLAS may be the missing piece. Forstner's planet seeding hypothesis at a planetary science conference in Germany, astrophysicist Suzanne Forstner proposed that interstellar objects could act as planetary seeds. In her view, young star systems don't always start from scratch. Instead of building them entirely from microscopic dust, they may capture interstellar objects, asteroid or comet-sized bodies that originated around other stars and were flung into space. Once captured into a protoplanetary disk, such an object provides a ready-made nucleus. Small particles in the disk are far more likely to accumulate on something already massive than to stick together in fragile collisions. The result is a rapid jumpstart to planetary growth, particularly for gas giants, which require large cores before the surrounding gas disperses. Her model suggests that massive stars are particularly efficient at capturing these travelers. Their strong gravity pulls in more seeds, and their disks, though short-lived, gain the jumpstart they need. Observations confirm that giants are more common around high-mass stars than around small, cool M dwarfs. Forstner's hypothesis provides a natural explanation. This idea doesn't invalidate existing theories like pebble accretion or gravitational instability, which also aim to explain its rapid formation. Instead, it adds another mechanism that may operate alongside them. Its formation could be a layered process with interstellar seed providing the first foothold and local growth mechanism finishing the job. Seen this way, 3IATLAS is more than an odd comet. It's a case study of how such objects might travel between systems. Sometimes captured, sometimes just passing through. If captured by a young star, it could become the foundation of a new planet. That possibility reframes interstellar objects not as rare curiosities, but as potential agents of planetary diversity across the galaxy. Implications and next steps. If Forstner's hypothesis is correct, it changes how we view both planet formation and interstellar traffic. First, it addresses the time problem in planetary science. Seeds from other systems could help explain why gas giants form so quickly. This is especially important for stars more massive than the Sun, where giant planets are surprisingly common despite short disk lifetimes. Second, it suggests that planetary systems are interconnected. Over billions of years, stars may exchange solid building blocks, meaning these aren't built solely from local material, but from a mixture of galactic ingredients. Our own Jupiter may trace part of its history to a body captured long before Earth even formed. Third, it raises the value of studying interstellar objects directly. So far, we know only 3, but with the upcoming Vera C. Rubin Observatory, astronomers expect to discover many more each year. That larger sample will let scientists test whether these bodies are common enough and massive enough to play the role Forstner suggests. Future missions could take the next step, intercepting an interstellar object. Spacecraft equipped with high-resolution instruments could analyze its composition, structure, and age, revealing whether it carries the traits of its seed. Concepts for such missions are already under discussion. Unanswered questions remain. How often are interstellar objects captured into young disks versus simply flying by? Do they survive long enough inside the disk to trigger runaway growth? And is the number of available seeds large enough to account for the observed abundance of giantdom? These are testable questions, and the coming decade may provide answers. Whether Forstner's hypothesis stands or falls, it highlights a need to treat interstellar objects not just as anomalies, but as potential keys to the story of planetary origins. Outro 3. IATLAS may be more than a comet. It could be a planet seed, a clue to how worlds are born. The theory isn't proven, but upcoming telescopes and missions may soon tell us if these interstellar visitors truly shape planetary systems. The cosmos is still full of mysteries, so stay tuned as we uncover them, one discovery at a time. Thanks for watching. Cool.